Today we're going to do an implicit differentiation problem extreme level. This is a super difficult problem, but very, very manageable once you have all the techniques from before: power rule, product rule, chain rule, etc. Today we're going to walk through a problem in full. If you can do this on your own and you understand this, you will be ready to take any calculus 1 exam or AP calculus AB exam. So let's get right into it. So implicit differentiation extreme. So just quick remarks that we use implicit differentiation when a function has more than one variable mixed into it. What I mean by that is it is something like x times y. Oops. All right. So, and if you need more, but kind of a basic example of what implicit differentiation is, go back to my channel. I've made a video or two on it. Go check that out. So let's get right into the problem. So we have x squared times y squared plus sine of xy plus ln x plus y is equal to y squared plus x. So immediately you can see that this function has multiple variables in almost every single term. So that is your initial kind of reminder to use implicit differentiation. So let's take this simple step by step. First step, let's differentiate both sides with dx. So we have d dx of x squared, y squared. And I'm going to go ahead and expand the d dx into every single term using the addition method. So I'll kind of skip one step. Plus d dx of sine xy plus the derivative of ln x plus y plus, oh, oops, is equal to d dx y squared plus x. All right, so that's step one, is take the derivative of the equation and expand it out. So let's go on to step two and differentiate each term one by one. Let's start with this term first. So we're going to do, I'm just going to do a little line here. D dx x squared y squared is equal to what? So out of the differentiation rules that we've learned before, we can see that this is a product rule. Because we have a function, a variable times another variable, like that. So a reminder, product rule is if you have the derivative of f of x times g of x is equal to f prime of x g of x plus f of x g prime of x. So let's apply that to here, and we have this as our f of x, and then we have y squared as our g of x. So let's go ahead and expand this. So we have f prime of x would be f derivative of x squared. So we have 2x times y squared plus our f of x right here, which is just x squared times our g prime of x. G of x is just y squared. So we have 2y dy dx. And remember, it is very important to add this dy dx to every single y term that you take the derivative of, because as stated in an earlier video, every time you take a derivative of any variable, I'm just going to make a little sidebar. So derivative with respect to x of, say, x squared, this is equal to 2x multiplied by d times the variable that you just took the derivative of, so we just took the derivative of x, over d times the variable with respect to which you're taking the derivative. So in this case, x. So d dx. And the dx over dx cancels out, so you're just left with 2x. But if you do the same thing with a y, you have y squared. This will be 2y multiplied by d times the variable which you took the derivative of, so y, over the derivative of the d times the variable with which you're taking the derivative in respect to, so dx, like that. And these don't cancel out, so that stays. And that is applied to every single term uh, in implicit differentiation. So this right here, I'm going to circle this. This is our first kind of, and actually I'm going to rewrite that as just a bit neater. So we have, this is all equal to 2xy squared plus, did I make a mistake somewhere? No, I didn't. Plus 2x squared y dy dx. All right, now I'm going to circle this. So this is, I'm going to say 1. I'm going to split this up. This is your 1. This is your 2, 3, 4. All right, so let's move on to number 2, which is the sine x squared, sorry, sine of x times y. So I'm going to draw another little dashed line. So we're going to take the derivative of sine xy yes. And actually, guys, I apologize. This y term right here was supposed to actually be a 3, um, and not a 2. So this actually ends up being 3y squared, and this ends up being 3x squared y squared. Sorry about that. Anyway, let's go continue on to this. So we have the derivative of sine x y. So here we have the chain rule again, because we have a function within a function, right? So I'm just going to make a little note of that. This is chain rule. And let's go ahead and try. So the derivative of sine xy would be cosine of xy, because derivative of sine is cosine, keeping the inner part the same, multiplied by the derivative of the inner, which is xy. So again, chain rule is the derivative of outer multiplied by the derivative of inner. So this ends up being cosine of xy. Oop, I wrote that. All right, let's look at just this part right here. So this right here is just another product rule, because you have two functions multiplied by each other. So this is product rule, and we already did product rule above here. So just to quickly do this, we're going to do d dx of xy is equal to So we have f prime of x, which is just going to be 1 times g of x. So it's going to be 1y plus f of x, which is just x, times g prime of x, which is 1 dy dx. So what that can be rewritten as is y is equal to, nope, y plus x dy dx. So let's put that all back into the full thing. So we have, I'm messing up all over today, d dx of sine x of y is equal to cosine xy multiplied by y plus x dy dx. And that is our final answer for number 2, our second term. All right, let's go on to the third term. So as you can see, every single big equation, I'm just going to highlight the original problem so it's easier to see. Every single big equation like this can be split up into multiple terms in which of easier magnitude. So we have a product rule, we have a chain rule with another product rule, and etc. So let's move on to the ln x plus y. So the derivative of ln x plus y. So for this, we're going to have to use chain rule. Because you have a function ln of something, and the inner part is another function. So we can rewrite this quickly as ln of u, where u is equal to x plus y, just for simplicity's sake. So the derivative of ln u is just 1 over u. However, we have to multiply by du dx because the u is what we just took the derivative of, over dx, which is what we're taking with respect to. However, that can make this whole thing complicated. So rather than using u, I'm gonna do it in a separate line of how to not use u in this case. But if we were to continue, we know that u is x plus y, so we can rewrite that as 1 over x plus y times du, so derivative of x plus y, which is d dx x plus y over dx. So to make this part a little simpler, we can, instead of going to this ln u, we can go directly into ln of x plus y is equal to 1 over x plus y times the derivative of the inner part. And sorry, I rewrote that twice. So you can kind of see that these two equations are equivalent, with u just making it simpler to see ln u is just 1 over u, because ln x, derivative of ln x is just 1 over x. But if you have multiple variables, it can be slightly difficult to remember that. So you can always use kind of a u substitution. But if that is too complicated in this form right here, we can always expand it out normally. So these two are the same. So let's continue and differentiate the inside of x plus y. So d dx of x plus y is equal to 1 plus dy dx, because derivative of x is 1, derivative of y is 1 times dy dx. Again, remember that. Now let's plug this back into the rest of the chain rule. So the full thing, d dx of ln x plus y is equal to 1 over x plus y times 1 plus dy dx. So yeah, so this is our our third equation. So now let's move on to the right side of the problem of derivative of y squared plus x. So this one should hopefully be a bit easier. D dx of y squared plus x. This is just, let's differentiate each piece. So we have 2y dy dx plus 1, and that's it. So that is our fourth and final component of the equations. So as you can see, we broke down this right here into 4 separate parts and took each one individually. And now let's combine and substitute everything back together. So, and this is kind of where calculus gets messy, but don't worry, just keep track of every single variable. So we have 2xy cubed plus 3x squared y squared dy dx plus cosine of xy times x dy dx plus y plus 1 over x plus y times 1 plus dy dx is equal to 2y dy dx plus 1. So that is a lot, but let's not worry too much. So we have our first term, 2xy squared plus 3x squared y squared, 2xy squared plus 3x squared y squared. That's term 1. This is term 2. This is 3, and this is 4. So we are just literally putting everything we've done together. So now the next step would be to expand everything fully, multiply everything out. I'm going to skip this step in writing and I'm going to go straight to the full expansion. If you want to try it on your own to see if you match my answer, go ahead and pause. But this is what the full expansion should look like. So we have expand. So we have 2xy cubed plus 3x squared y squared dy dx plus x cosine of xy dy dx plus y cosine xy plus 1 over x plus y plus 1 over x plus y dy dx is equal to 2y dy dx plus 1. So that is the fully expanded version where we multiply everything through. And that is very important just because the final or the next step was when we're trying to isolate dy dx. We have everything in its own separate term. So, like I just mentioned, let's move all the dy dx terms to one side. And what we get, so move dy dx to one side. So what that ends up looking like, we have 3x squared y squared dy dx plus x cosine of xy dy dx plus 1 over x plus y dy dx minus 2y dy dx is equal to 1 minus 2xy cubed minus y cosine xy minus 1 over x plus y. So now let's factor out the dy dx. So this can be rewritten as dy dx is equal to, nope, it's not equal to, my bad guys, dy dx factored out, which is multiplied, okay, sorry guys, it's been a long day, 3x, that's a 3, 3x squared y squared plus x cosine xy plus 1 over x plus y minus 2y is equal to 1 minus 2xy cubed minus y cosine xy minus 1 over x plus y. So now let's divide both sides by this term so that we can isolate dy dx as our final answer, to which we get dy dx is equal to 1 minus 2xy cubed minus y cosine xy minus 1 over x plus y, all over 3x squared y squared plus x cosine xy plus 1 over x plus y minus 2y. And that is our final answer. So even though this was a very long and tedious process, I hopefully that made solving all types of derivatives easier when you have a problem of this difficulty in this many terms. Don't panic. Split it up into as many components as you need. Treat each component individually due to the linearity rule where you can just add them all up, and then expand them and isolate for dy dx to get your final answer. Thank you and have a great